Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be starting chapter 6. We're really going to be diving into the ideas of how we can quantify and describe the concentrations and identity of a molecular species. And one of the best ways to do that is to do a quick review of molecular weight or molar mass. So one of the big things is once we have our molecular formula that we've been looking at over the last several chapters, what we can do is relate this to a number of physical properties. But one of the biggest things we almost always want to start with is by determining the molar mass of a species. Because once I've got the molar mass, I can try and once I know the mass of a species, I can determine the amount, which will be very important for chemical reactions. It will also let me start determining the mass of all the individual elements, carbon to hydrogen to oxygen. And these are things that are often measured because we often measure things in mass and we often need to relate chemical reactivities in moles. Also, this will let us go ahead and connect all of our various properties to things like density, or when we link it to things like solutions into important concentrations. So we can often be dovetailing molar mass and density with Avogadro's number and concentration measures like molarity and percent weights and all sorts of things. And trying to apply these more numerical descriptions to our molecular species is going to be a major focus of this chapter. But it all starts with good old molar mass or molecular weight. You'll often see it with one or the other, but they can really be used interchangeably. And as a quick review, we can determine the molecular weight of a species simply by looking at the molecular formula and then adding together the atomic weights of each of the component elements, and then multiplying that by the number of each of those elements present in the molecule. So let's go ahead and start by looking at what's the molecular weight of our good old friend ethanol. So ethanol's got 2 carbons, 1 oxygen, and 6 hydrogens. So we can find the molecular weight by taking twice the molecular weight of carbon, adding in 6 times the molecular weight of hydrogen, and the molecular weight of oxygen. So we add these all together. Pay attention to your sig figs. By tendency, I tend to use 2 decimal points. So my resulting number will be good to 2 decimal points. And when we add this together, we find the molecular weight of ethanol is about 46 grams per mole. This is a little hard to kind of get an idea of what that means. So one of the things I often like doing is trying to inverse this and figuring out how many moles of a given species are in a 1 gram sample. So essentially the weight of about a dollar bill, or again, another fairly light thing, a paperclip. So when we do this, 1 gram of ethanol, we divide that by the molecular weight, and we find that we've got about 0.02 moles of ethanol. All right, that's kind of gives me an idea. Not a whole bunch of moles, but enough. Now we can go ahead and try and apply this to a little bit more complex structures now that we've got an idea of things like Lewis structure. So here's the molecule tryptophan. It's a very important amino acid. It's the one that makes you sleepy when you eat turkey, because turkey has lots of tryptophan, and tryptophan can essentially become melatonin in your system. So let's go ahead and try and figure out what's the molecular weight of this tryptophan. So the first thing we're often going to want to do is go from this simplified Lewis structure to writing out all the carbons and hydrogens. Because it turns out it's really easy to miss 1 or 2 if you don't. So when we do this, we find we've got 11 carbons, 2 nitrogens, 12 hydrogens, and 2 oxygens, both in that carboxylic acid on the end. So we can use this to find the molecular weight, adding together each of the individual components. It is worth noting that oxygen is 16.00, so I am not losing any sig figs. When we do this, we find we've got a molecular weight of about 204.25 grams. So this is about this is about 5 times the molecular weight of ethanol, which means that we've got a much fewer moles. In this case, 1 gram of tryptophan generates about 0.005 moles, or 5 millimoles. And this is really worth noting that as you get to fairly large molecules, even decent weights will tend to still give you fairly low number of moles, which has some really important consequences when we start getting into chemical reactivity. So this is how we can make use of molecular weight. But a lot of times you have empirical measurements, you have masses, and we want to try and figure out how we can relate that to molecular weight. So next time we're going to be diving in to the relationship between molar mass and percent compositions. Till then, take care.